Okay, so this is a recording about buffers, and I'm going to discuss two source codes. One is buffer1.c, and then the other one is buffer2 circular.c. Now, I apologize if this is some repetition of the stuff that I said in class. I just want to make sure that this video is complete. So if you have two devices, you have device 1 and device 2. And device 1 sends data for device 2 to receive and process. Let's assume that device 1 sends data 1, data 2, and data 3. So these are bytes. So I'm just showing you at the byte level. And now device 2 obviously has to have some receive mechanism, be it USART, be it any other mechanism for receiving. It has to receive the data as it comes in. So if device 1 is sending at a high baud rate and device 2 cannot operate at that baud rate, that's not the case we are considering. So I'm assuming that the receive side of device 2 is able to receive the data, but the processing of the data takes a long time. So let's say data 1 gets processed here, and then it starts processing data 2, and then it starts processing data 3, right? Now, um, and obviously here you need a buffer, right? Because when you receive 1 and then followed by receiving 2, if you have only one place to get the data from device 1, then device 2 would be lost because you still need that place to process data 1. So you need a buffer. But the point is, if device 1 wants to keep going with 4, 5, 6, then with no stops and device 2 is doing processing at a slower rate, then this is not sustainable. The buffer size that you need would grow to infinity, and obviously you can't handle the situation. But as soon as data 1 is done processing, you can flush that from the buffer, right? So if I assume that I have a buffer of size 4, then the first location receives 1, the second location receives 2, the third location is going to be received in location 3, but guess what? We can discard 1 because we're done processing it. So my buffer right now has only 2 stored in it. It has room for 3 more. So I can receive 4 right here, but then let's say there's a lull and I don't receive anything, and then this is processing 4, maybe 5 can come here, right? Because the time that 5 is here, I've already processed 1 and 2, so I'm only holding 3, 4, and 5 has room. And in fact, even I could have received 6 by this time, right? By this time I could have received 6 because my buffer is of size 4 and I have room for keeping 3, 4, 5, 6 at this point. But I didn't make it too aggressive, so there is some slack with device 1. So in this scenario, my buffer of size 4 is not being fully utilized. I still have empty locations in my buffer, and it's not strained too much. Now, I'm not interested in implementing stuff on the device 1 side. Okay, we're only going to look at device 2, and there's going to be some mechanism that receives data and some mechanism to process data, right? So the receive side of it would be done, as I said, through USART or any other standards. The point is that channel that is listening for data is constantly listening to the data that is coming in, regardless of what main is doing. And then when it receives all the 8 bits of the data, it's going to raise an interrupt and you're going to be brought here. And you would just need to say new data that you read either from USART or from a parallel port like port B. Get that new data, put it in the buffer. Okay, and this is very abstract. I'm not talking about, an array or the index of the array. Well, for now, let's just say, you put it in the buffer and you get out. Right? You don't need to worry about processing the data here. And then in the main, obviously you do setup first, setting up this interrupt, listening for the channel. And then you have an infinite loop. You have a while 1 that says, do I have new data? And that's the translation of that would essentially be, is buffer empty? If it is, then skip the rest of this loop and go back to this while loop, listen for stuff. Okay? Else, your data is going to come from the buffer and then process data, which presumably is going to take a long time, and then go back to this while one, check to see if is the buffer empty or not. Right? So there has to be a signaling between interrupt and is buffer empty and main, so that main can take a look at that data and say, is the buffer empty or not. Now, I would have implemented this using UseArt, but because UseArt is not so easy to simulate, I'm going to cheat. I'm going to use a much simpler communication mechanism in which data is transmitted through a parallel port. So what I can do is I can have a control signal that says data ready, new data ready. So this is a control signal, and it sends a pulse when it provides the data on, and let's limit ourselves to 3 bits. So it puts, device 1 puts the number 5 on these lines, and when the new data 5 is ready, it just sends a signal on this control signal here, and we can connect it to our int 0 pin, and these could be on RB0, RB1, RB2 to get the data and simulate. So essentially when you receive an interrupt, then basically your new data is going to be in port B, put it in a buffer, and if buffer is an array, just increment the pointer that says, you know, how many elements I have in the buffer and so on and so forth, and then, you know, you're set. You can receive new data. Now, the first version that I wrote is called buffer1.c, and we're going to take a look at the source code in a minute. But let me first show you in a cartoon way how it works. So let's assume that your buffer has a size of 4. Okay, so these are the indices of the buffer, and let's say at the very first clock cycle you receive the data 3. There has to be a pointer that says this is the first empty location in the buffer that I have here. Okay, and then let's say before main gets a chance to process the data or fetch the data from buffer, let's say the data 5 arrives. So you increment that index pointer. Let's say the data 4 arrives. You increment the pointer. And if I receive another data, let's say I receive data 1, then my pointer will be pointing to here, which is not a valid location. So this is going to be a buffer overflow. If new data comes in, essentially I have to drop it because I don't have room for new data. And, you know, in my interrupt routine, I should just say ignore that data, right? But let's assume your buffer is here, and if the buffer is here, let's say main gets to that point that says is buffer empty or not. Now for the buffer to check if buffer is empty or not, you have to just check to see if this empty buffer location index is 0. If it is 0, it means that the buffer is empty. If it is not, the index would be pointing to here. If it is not, then it means that you have something in the buffer, right? So main then basically is going to say decrement index and read the value of 1, and now index would be pointing to 3, which means this is the first empty location that I have and I can access. So you can go ahead and receive a new data, which could be 2, and overwrite it on this location, and now index would be again pointing to 4. Sorry, this became such a busy figure. So your main is basically going to, sorry, I made a mistake. The code, what I just described is a buffer policy called LIFO, last in, first out, in which, when I had one inserted in the buffer, one was the one that, was read out. The last one that was pushed in was the first one that I took out. But the code that I wrote is not like that. The code that I wrote acts like this. The code that I have is FIFO, first in, first out. So forget about this picture. So you have 0, 1, 2, 3. 3 comes in, 5 comes in, 4 comes in, 1 comes in, and now index is pointing to this location. And now let's say main gets to that point that says is buffer empty or not. Again, it checks to see if index is 0. If it is, it means that the buffer is empty. If it is not 0, it means that there is data. So what main does is it fetches data from here. So 3 is going to be the data. But then what it does is it shifts the values. So it's going to have 5, 4, 1, and this 1 remains here, but it would be junk. And then the pointer is going to be decremented to 3, so that if new data, let's say 2 arrives, then 2 is going to overwrite this 1, and now the index is going to point to 4, which indicates the new empty location. So if main now catches up, if there is no activity from device 1, then main is going to fetch the value of 5 as its new data, and then the buffer is going to look like 4, 1, 2, with this 2 being junk because pointer is pointing here. And then it reads another data. 4 would be the new data, and then you have 1, 2. This 2 is here, but it's junk. And 2 is still here. So we don't overwrite data with 0 because, I mean, there is no difference between 0 or 2 or any other number, right? I mean, you're not going to read this value anyway. This is just ready to be overridden by new data. And then if you have another data read from main, then, 1 going to be the new data, 2 is pushed here, but now this is the index pointer. And again, if you read 2, then essentially what happens is that your buffer array data structure is going to look like this, but then the buffer pointer index, the first empty location index, is going to point to 0, location 0 in the buffer, which means my buffer is empty. Right? So you're not going to keep this 2 in main. Main is going to look at this index, and this index indicates that you are you have no data in the buffer, and if new data arrives, it's going to overwrite this first 2, and index pointer is going to go to 1. Now this is very easy to implement, easy to understand. It's very inefficient because what you're doing at every step is that you are shifting these values. And imagine that if this buffer is long, if you have 100, if you have room for 100 elements, then the loop that is going to do the shift is going to do 100 steps of loading of the values. And that's going to be very slow. We don't like this. But before I go to the more advanced version of the buffer, let's go to the code and simulate it. So this is the code, buffer 1. And I can go ahead and show you the source code. So buffer size is set to 4. Empty location index is that index that I talked about during this. And so this index is called empty location IDX index. And in my buffer, which is a character here, is of size buffer size. Now my int 0 interrupt is going to first clear int 0 if, and then it checks if the empty location index is less than buffer size -1, then it is going to, so that means that I still have room for this. And I think this would be, it would be okay if I write buffer size and not -1, because this index could go all the way up to 4, and I would be okay. Let's go ahead and do that. All right, so if there is still some empty location, I would put the new data, which is in port B, those 3 bits. I'm going to put it in buffer of the empty location index, and I'm going to increment buffer empty location index after this operation. So this could go up to buffer size. Okay. Now else means that my buffer is full. So just drop the data. Don't do anything. Don't increment this buffer index. Don't fetch the data from port B. Just let it disappear into the ether. My setup is basically setting up port B as input and then enable the int0 IE. Now there's this subroutine called read from buffer, but let me skip it for a moment. Let me show you the main. So in main, I just do setup, and then this could also be int, so I don't have to make it too slow, the computation. So I set up, this is the while loop that I had, and I say if empty location index is 0, continue. So continue in the C language inside the loop means that skip the rest of the instructions in this iteration of the loop. So skip all of these operations, go back up here and check the condition. Okay, so if the buffer is empty, continue, don't do anything. And then character X is read from buffer. That's the function that was above here, and I skipped it for the moment, and I'm just computing sum plus equal X 4 times. I'm doing a silly computation here just to allow myself to insert and inject new data while I'm processing one data, just to show you, how the buffer fills and empties. Now, what does this read from buffer do? Remember, you have already checked to see if the buffer is empty or not, and the answer was no, the buffer is not empty. And just to make sure that I'm not going to make a mistake, there's this function in the C language, and if you want to use assert, you have to say include assert.h. So what assert.h does is during debug time, not when you compile the code for release, during debug time it checks this. If this condition is false, then it's going to stop the program and show you an error message on the screen that says, hey, this condition wasn't met. And putting asserts in your programs as a programmer is really important. You can't imagine how much headache it saves you. So every function that expects the buffer not to be empty, for example, has to check to see if in fact the programmers who called this function called it on the right conditions. All right, so, but if you didn't understand anything from this assert thing that I said, maybe ask me later. It's not crucial for understanding this code. All right, so, and remember, we always read from buffer location index 0, and now you have to shift the values. Okay, so to shift the values, I go from 0 to empty location index -1. These are the new destination locations for that. And let me just make sure. If empty location index is 4, then this is going to go less than 3. So it's going to be 0, 1, 2, and it's going to fetch the value of I plus 1 into I. Yeah, that's correct. So I think this is correctly implementing the shifting of the values in the buffer, and this is the main culprit, right? So if your empty location index is 100 or 1000, then this loop is going to take a very, very long time, and this is unnecessary. I'm going to show you in the next implementation of the buffer. And this is crucial too. You decrement empty location index to just indicate that the pointer has to be moved to the right, and I have more room for writing new data. All right, so let's go ahead and simulate the program. And in the program, in the stimulus, I provided these asynchronous pin actions. Now, ideally, you would have used the pin register actions to say at time 200 microseconds, port B has to be a value of this and that. But it never worked for me. I tried simulating it with this pin register actions, but it wouldn't change port B value. So let's just be happy with what we have here. And in the variables, I'm showing buffer, and I can just expand it to see buffer location 0, 1, 2, 3. And I have the empty location index shown here, and I have port B value shown here. So here, this would be doing nothing, right? I mean, this would just continue and keep being, you know, stuck here. The while loop is not doing going to do anything as long as empty buffer location index is 0. Now, what I'll do is I'll give it the value 3. Let's use the same values that we used here, 3, 5, 4. So I gave the value 3 on port B. And we can check that. Yes, port B is now 3. And now I can give the pulse on this int 0. So what happens is that I go to, what happened? Yeah, I'm brought to the interrupt. And right now my empty location, it might be a good idea to just, you know, recreate this animation here. So I have 0, 1, 2, 3, and I'm just about to receive the value 3 here. Okay, and my first empty location buffer index is here at 0. So here what will happen is if empty location is less than buffer, which it is, I still have room, then my buffer is going to be the value of port B, which is 3, and I'm going to increment the buffer index. So this buffer index is now going to go here, and I have the value 3 in here. So if I do this line, yes, you can see that buffer 0 has the value 0x3, empty location index has a value of 1. Okay, so let's go, and this is going to say continue, but before, So before I do the continue, let's change the value to 5. So it is 3, so I need to do this and then do this and then give the interrupt. So I'm brought here. Now the value 5 wants to be placed in the buffer. It is still empty, so I can just do buffer plus plus. So you can see 3, 5 are here, and empty location index is now changed to 2. So right now I'm at this stage, 3, 5, and the empty buffer location is pointing to index 2. All right, and let's go ahead and give it a value of 5. So right now it's 5, so I'm going to click this and then give another pulse. So immediately I come back here and then I increment the buffer. So this has a value of 4 and empty location index is 3. So I have written the value 4. And note that main has not had a chance to even read one single value up to this point, right? So the index is now pointing to 3, and let's go ahead and give it yet another data. Let's give it the data 1. So if it is 4, then it means that this is 1. All right, so I gave it the value of 1 on port B, and I still do have a space, so I put buffer into empty location index. So my buffer is now 3, 5, 4, 1, and this is the picture right now. 3, 5, 4, 1, and the buffer location index is at 4, which is outside the bounds of the array. So let's go ahead and give it yet another data. Let's give it a value of 6 and give the pulse, and we're going to see that the program is going to check if empty location is less than buffer size, which it isn't, and it's going to just skip that data. So else happened, in which I just dropped this data. I don't have room for placing it. Now let's see what main does. So main now checked the empty location, but it checked the empty location way back here, right? At this step it checked, but before it got a chance to fetch the data, interrupt happened, the interrupt happened, and I filled the buffer. Now, the read from buffer, let's go inside it and see what happens. So I'm about to read the very first item. so x is buffer 0. Buffer 0 is 3. So that's the value that I want to have. And here I'm going to put buffer 0 equals buffer 1. Buffer 1 equals the value in buffer 2. Buffer 3 is equal the value in, sorry, yeah, 2 would be the end of it. So as I do this, just note here, I don't know if you can read this or not, but we have the values 3, 5, 4, 1. And the first element became 5. The second element became 4. The third element became 1, and you exit the loop. So I have 5, 4, 1, 1. So this is what happens. So this is placed in X, and then my buffer now looks like 5, 4, 1, 1, and the empty location index is now set to 3, which is the index here. So 3, 1, 2, 3. That says, you know, new stuff would be put in here. Okay, so I return X, and now if let's say the data 6 happens again, or data 7 happens here, my port B right now is 3, so I can just assert this to make it 0. So int 0 pulse. So while main is processing the first data, while main is processing that element 3, I just received new data 7. And that data 7 comes here. Is my buffer full? No. So I say buffer of empty location equals port B, which is 7. So now I'm going to overwrite that junk 1 with 7. So 5, 4, 1, 7, and then the index is going to go to 4. All right. So let's go ahead. So 5, 4, 1, 7, and the empty location index is 4. All right, let's go back to main. So main is doing its computation, and for now let's give it a break and not send it new data. Empty location index is not 0. I still have data. So now this is going to read the value 5 from the buffer. So I'm not going to single step through it, just show you what happens to the buffer. So 4177 is the value in the buffer, and the index is 3. So 5 was read as X. So I have 4177, and the index is here. Let's go ahead and do the step over. And now I didn't insert new data, so 4 is the value that I'm going to read. So if I do that, then my buffer becomes 1777. So my buffer became 1777, and my empty location index is now 2. So 0, 1, 2, this is the index pointer. I hope you get the point, right? I mean, hopefully everyone has gotten the point how this buffer thing works. And that's, you know, our simple buffer 1 implementation. So let's go ahead and load the buffer 2, which is a circular buffer, and simulate that. So I'm going to show you how buffer 2 works. The code is here. So now instead of having just one pointer and doing the keeping track of the end of the buffer, I'm going to have 3 variables. And the way that it works is like this. So I have a buffer, and again it could be of size 4. Now I maintain 3 variables. One is going to be the write index, the other one is going to be read index, and the other one is, so this is the read IDX, write IDX, and I have num elements in buffer. Let's just call it num e. Okay? Now at the very beginning, these are all set to 0. Okay, the buffer is empty. But let's say you insert 2 elements into the buffer. Let's say you put, let's use the same values, 3, 5. Let's say you place 3, And now your write index is going to point to here. So this is my write index. This is my read index. So W index is now set to 1. Read index is set to 0. And num elements is now set to 1. I have one element in my system. Now, what happens is I send, let's say 541. Okay, if I send 541, sorry, what did I do? 3541. Okay, so 3, 5, 4, and at this point the write buffer is here. Okay, and the number of elements is going to be 3. Let's say you insert another value into the buffer, 3541. Now, instead of write staying here and saying that I'm full, it's going to go to here. So both W and R are pointed to this. So W is 0, read is 0, number elements is 4. Okay, so we rely on this num elements to tell us if the buffer is full or not. And then read, let's say main starts reading the data. So if main reads the value 3, then the read pointer is now going to point to 5. And my write pointer is still going to point to this 3, which is now junk value, right? I've read it and processed it. And num elements is going to be 3. Let's say main reads another one. So this is going to be the read index, this is going to be the write index, and num elements is going to be 2. Okay, and so you can see that, you know, at this point R was to the left of W. At this point R is to the right of W. So this is like a circle. They move in a circle. And if reads 4 and it reads 1, it's going to point back to this 3. In the meanwhile, write might have read what were the values that we had? Oops, sorry. Yeah. So the values in the previous example, when we read 3, we inserted 7 after that, right? So let's say you insert 7. So 7 is going to be written here. Then W is going to point to here. And it's written 5, but it's junk. And read is going to be ready to read 4 and 1 and then 7, right? So number of elements here is going to be 3. Okay, so I hope you get the picture. This is basically how it's going to work. These pointers wrap around. You can't rely on R being to the left of or to the right of W to determine if the buffer is empty or not. And of course, I mean, the other thing that you want to avoid is reading too fast, right? So if your buffer is, if your main reads 4 and then it reads 1, and the R buffer wraps around to here pointing to this 3, your main should not read anymore, right? So your main should always check this NE. If it is 0, don't read junk value that you've already used. Wait for the write pointer to write a stuff to buffer and move forward, and then read the stuff. So here's, you know, the rest of the code. So we have these 3 pointers: read index, write index, num elements in buffer, and the interrupt routine is going to be similar to what we did before with minor changes. So the first change is you check num elements in buffer for buffer size. In buffer 1, you used to just check the buffer index. You checked empty location index less than buffer s, but that's no longer useful because it wraps around. You check num elements in buffer if less than 0. And then you would say buffer of write index plus plus equals port B, write index % buffer size. Why do I do that? Well, you just want to do modulo operation. So if your W is 3, all right, and this is the picture, so 0, 1, 2, 3. Let's say your W buffer is here. When you do W++, it becomes 4, but you want it to wrap around to 0, so you can just say W% equal 4, which is the buffer size, and it becomes a value of 0. So this percent is the remainder operation in C, and if you divide 4 by 4, then W is going to become 0 here. But if the value of W is 1, 2, or 3, if you do %4, it remains the same. It doesn't change. So that's why we have this statement here. And then you increment num elements in buffer, which is what you check to see if buffer is empty or too full to drop data. And here there's no change. In the read from buffer, what you do is your X doesn't read from buffer 0. It reads from read index plus plus, and you do the same modulo operation to wrap it around to 0 if it becomes 4, and you decrement num elements in buffer. And in main, you say as long as num elements in buffer is still 0, continue. Otherwise, just read from buffer and get the value that you have and move forward. I don't think we need to simulate this. I think it probably is clear enough, but I encourage you to simulate it. So you saw how I simulated the first one, the buffer one .c. Go ahead and simulate this, and the point here is in the stimulus you just add these RB0, RB1, RB2, do the toggle, and int 0 pulse high. You just change these values, and if you want, just do one single step to see the value of port B, see if this is the value that you want. If you made a mistake, maybe do another toggle. I haven't done the int 0 pulse yet, so you can change port B values until you're happy with the value, and then you give it the pulse of interrupt, and then it goes to this location. And while you are here, right after you read the port B, feel free to give it more values. So instead of a value of 2 on port B, I can give it a value of 6 by toggling RB2 and then doing the int 0. So right after the interrupt gets out, it's going to immediately go back in, and then it's going to write the value of 6 into the buffer, and you can see that it has 1, 7, 2, 6, so on and so forth. So basically that's it. That's how a circular buffer works. The one last point that maybe I can talk about would be sometimes people prefer to set the buffer size to be a power of 2. So it goes from 0, 1, let's say up to 63, right? And that wraparound operation of widx % equal 64, instead of this operation, which might be slow and involve some division operations, instead of that, people can just say widx and equal 0b, and then you have a bunch of 0 zeros, 0, and then so you only need 6 bits to store a value between 0 and 43, so they do this, right, which is essentially 63. So you can just say w index and equals 63, and essentially what happens if your number becomes 64, which is 1 0 0 0 0 0 0, you're ANDing it with 0, so it automatically wraps around to 0. So this, usually microcontrollers are much faster doing an AND, a bitwise AND operation compared to the % operation. So that's one trick that people use and prefer buffer sizes that are powers of 2. But other than that, if you're happy with this, then the buffer size could be anything. All right, thank you.